Okay, class, good to be with you again. This is the video lecture to accompany Whitlock and Schluter Chapter 4. It will differ a little bit from the chapters 1, 2, and 3 in that there's a greater amount of statistical concept. I think there is something here that probably you haven't seen before. So I'm going to slow down a little bit and just try to zoom right into the concept. To start, we're going to move right into the example from the book, which I think is a fine example. We have a data set here that consists of all of the lengths of the genes on the human genome at a certain point in time. Now I'm going to replicate some of the stuff in the book. It's on R, and it's the Whitlock-Schluter text examples file that I've created here. If we just look at the raw histogram, you'll notice it's terrible, and that's because there's some outlying data points. We could look at a box plot of this, box plot gene.length, and you'll see the box plot's not very informative because this particular one is so far out. You'll notice there's a lot of outliers. So I'm giving you a nice piece of syntax here. This is a histogram, looks much better, and we're just taking a chop here at genes over 15,000. We're cutting those off. Now we're looking pretty good. Took a little bit of experimentation to get down to that. Now, I'd like to note that what we have is a population, namely we have all of the genes. So let's take a look. Length of gene.length. We do not want to display this on the screen because there's 20,290 values there. They're big. If we just look at the first part, then you'll see, okay, first 6 of them, we've got those values. And we don't want to see 20,000 numbers coming on the screen. It won't handle that. Since it's a population, I can calculate its population parameters. That's why I've called these mu, sample size, that's total sample size now, and sigma, that's population standard deviation. These are the actual parameters that we have. Okay, now, let's see, little note on the standard deviation. I calculated that by the standard deviation formula. Okay, so if we just use the default R's SD command, it is different. That's because it has that n-1 in the denominator. Okay, so if you put that n-1 in the denominator and you use mu, then we're going to get this value. Of course, SD actually uses x bar and then n-1. So, okay. Now with that, let's take a look at some samples from these 20,000 genes. And I want to take samples of size 100. And furthermore, let's just do one of these. Just take a look at one here and unpack that line. I've actually cheated on that line, and I've called 3 commands. I've called take x as a sample of size 100 from gene length. Okay, so if I just pop out here x, there it is. Then I tacked on a couple of other commands. I said also, separated by a semicolon, do a histogram, and then calculate its mean. Cool. Okay, histogram. There it is, and then mean, there it is, 2,488. Well, what if we do that again? Oh, different sample, different histogram, different mean. Again, different sample, different histogram, different mean. Again, and we're going to see this happen over and over. So I can speed this up by calling a command to give me a 2x2 window. And I've got 4 histograms. Again, they're all different. That one's purely skew right. That's an interesting one. We didn't hit any of those rare outlying points that gives me the extreme looking histogram. And we can do all that. If I want to just close the whole thing I'm going to hit this, boom, that shuts them all down. All right, now let's get into the nub of it here, and I'm just going to run this next block of code and then comment. This does not look like the skew right distribution that we saw before, and it says histogram of X bar. What happened? Well, what happened was I took a sample from the same set of all genes. I took size 500 now instead of 100. Could have done 100. But then, instead of plotting the sample, I went ahead and just calculated the mean of that sample, and I stored it, X bar sub I. So X bar, if I look at its length, should be 1,000. Okay, there's 1,000 means in that thing. Here are the first 6 of them. Okay, now I'm plotting a histogram of all 1,000 means. And you'll notice it's mound-shaped. It's not skewed. Okay? This thing, first of all, is the sampling distribution of the means of sample size 500. Okay, let's jump to the notes. Okay, first definition here in the notes is sampling distribution. And the sampling distribution is the probability distribution of values for a statistic. Okay, so to boil it down really simply, if we have X, okay, where X equals gene length, then we have skew right distribution, something like this, depending on how extreme. But if I take the mean of a sample of size 500, and let's just put that on the side so we note it, 500, then X bar looks like this. Okay. Now, that's the difference between the distribution of X and the distribution of X bar. Okay, X bar is called a sampling distribution, X, regular old probability distribution, and that's the relationship. If I were to take other statistics, such as standard deviation or median, I would get a different sampling distribution, all coming from the same, what I call a parent distribution. So let me write that, parent. Parent, and then this one is the sampling distribution. Okay, now that covers that part. Let's see what else I have here. Okay, so I have a cleanup command, remove X and X bar. It's a good idea to do that. If you notice here, here's X and X bar. If I click this, boom, they're gone. Okay, just cleaning things up. Okay, let's take a look at this standard error notion. We have talked about standard deviation, and the standard deviation is the average distance from the mean. So for X, we have standard deviation, but for X bar, well, let's put it this way. The standard deviation of X bar turns out to be the population standard deviation of X is denoted by sigma, okay? That's the true population value, and we had that, and we called it sigma, and it's 2036, okay? So when we come over here, that's 2036. Now, when we take our SD for the sampling distribution, it turns out, by a theorem that I'll talk about in Chapter 10, that it is the parent's population standard deviation divided by the square root of the sample size. This is phenomenal. Phenomenal. There's an order that the Lord has placed in the world that pops out here that is really amazing. It did not have to be this way. This happens for any random variable x. It's amazing. Okay, so now what that would mean is sigma, we've got 2036 divided by square root of 500, and that's going to give me a number. So let's take a look here. And if I do sigma divided by square root 500, then I've got about, let's just round it off to 91. Okay, and I'll write that number down, 91. But is that what really happened? Because after all, I have 1,000 samples of size 500. Let's check it out. SD of x bar. This is the list of those 1,000 values. Oh, I deleted x bar. Okay, let's just run that baby again, and do it. Boom! I've recreated x bar. No, that's not the x bar I want. There we go. X bar. Slightly different samples, slightly different distribution. Not a big problem. It's 90. Okay, it's one off. This is an estimate of the true standard error that we would get if we had the original sigma. So we get a 90 in our estimate. Very, very accurate. Great. Okay, so that gives us the relationship between the parent and the sampling distribution. The measure of variation of the parent is standard deviation. The measure of variation of the sampling distribution, since it's related to standard deviation, we're going to call it standard error. Okay, population standard deviation, we'll call this standard error. And so that's where this name comes in. It's simply the standard deviation of the parent. And let me note, just to be very explicit, we use the formula sum of xi, which in this case was an x bar, minus the mean. Okay, that's the mean that we calculated from the 1,000 observations, squared. We divided that by, in this case, we'll say 1,000 minus 1, and then we took the square root. Okay, and we got ourselves about 90. Wow, that's pretty awesome. Okay, as statisticians, we make judicious use of this fact. Now, we've just looked at how the population standard error is the standard deviation of the parent divided by rad n. For estimation purposes, we use the sample standard deviation right here, and then we divide by the square root of n. I enjoy using SDE, and I typically do that in my notes. The book, Whitlock and Schluter, they use SE. These are the same thing, so please don't get confused if I slip and do that. To illustrate, if we have samples of size 20, then that would be the population standard deviation, 20, 36.9 over rad 20. That number turns out to be about 455. We got 0.5. If we do over rad 100, we're obviously going to get 203.69, right? And then for the 500, we got that one already computed. Let's just do, say, this one right here on the computer to emphasize one more time. What if we reduced our samples to size 100? Okay, so in my little loop, I'm just going to go in and change that size from 500 to 100. We'll keep 1,000 observations. That looks good. And I'm just going to rerun. Notice that I'm moving here from 2,400 to 2,900. That's approximately the range. See what's going to happen. Boom! The range jumped from 2,000 to 3,500. And we have this little skewness that's popping in. That's a residual from the parent, which has some extreme skew. Let's take a look here at the SD of x bar, 204, and we predicted 204. Again, amazing accuracy, which we will use in our next segment to explore this new statistical concept of confidence intervals.